So we're starting with true false like we usually do. First one is A. Amides can act as bases. You should be aware of this, but in case you forgot or like you were confused by it, this is an amide. And this is an amine, so they sound very similar, but they're very different groups. In case you were considering that. Give it 10 or so more seconds. Okay. So 2 of you said true and 1 said false. This one is false, and I think you talked about it a bit during lecture on Tuesday. Basically, like amines can act as bases because they have this lone pair on them. So amines, like by themselves, are good as bases. Amides also have a lone pair, but they're not good bases because I'll draw it the other way. Because they're next to a carbonyl, you can draw this resonance form with the amide. And what do we say about a structure if it has more resonance forms? Like, what does that tell us about the stability of the structure? Is it more or less stable? Like comparing this amide with resonance to the amine without resonance, what could we say about the amide? It's more stable, yeah. More resonance forms or less reactive. Those two basically mean the same thing. So because the amide has resonance, it's more stable, so it's less reactive than the amine without any resonance. And that is sort of a way to explain like why an amide is not going to be a base, because it's less reactive. Keep going, but if you have any questions about the first one or anything else, feel free to stop me. Now going over B, electron withdrawing groups increase the base strength of an amine. Is this true or false? Get it 10 or so more seconds. Consider what bases are, like what they need to be a good base and what a withdrawing group would do to that. Okay. So all of you said this is true. Now, if we were talking about acids, this would be true. Like if we were saying electron withdrawing groups increase the acid strength of something, that's correct. But if you're looking at a base, like let's just say I'm looking at this amine as a base. Like in order to be a base, it needs to donate this pair of electrons to take a proton. Like that's what a base is. It's an electron pair donor. But if we have an electron withdrawing group, like a halogen, like chlorine as an example, because it's withdrawing, like it pulls electrons towards it. So it's pulling electrons away from the base, which makes it a weaker base because it's taking the electrons away. So That's the kind of logic we could think about for this. Electron withdrawing groups take electrons away, so make bases weaker. And this is actually the same logic like we saw before when we looked at acid strengths. Just in the past, we'd be looking at like if you were trying to talk about the acid strength of like an alcohol, then you would be looking at the conjugate base form of it. Remember this? And then we'd consider like whatever affects the conjugate base, like that has an effect on the acid too. So this isn't really new. It's just like we're focusing on the base now. We're not like working backwards from the base to the acid. But if you remember the concepts from before, it's the same ideas. So this one was false because of that. An electron withdrawing group will make a base weaker. Next one is C. Propylamine is a weaker base than dipropylamine. I would suggest drawing the structures unless you have a really good visual representation of it in your head, especially like if you had this kind of question on a test. This is propylamine. Like I would recommend drawing these yourself, but this is propylamine and this is dipropylamine. So it's just an extra propyl group. And consider what the extra propyl group would do to the amine, like if it would increase or decrease the base strength. Okay, I'm going to end it in a second. So most of you said this was true. This is basically the reverse logic of like the electron withdrawing group, like a halogen. Pulling electrons away from the base makes it a weaker base. Remember, we've talked about how alkyl groups, like a propyl group here, are electron donating groups. So they push electrons towards the rest of the molecule. So like in propylamine, we have one alkyl group donating electrons, and then in dipropylamine, there's two of them. So there's like twice as much donating effects. So that makes the base stronger because you're donating electrons. So EDGs make bases stronger because they're donating electrons to an electron donor. So this was true because of that. Propylamine has less electron donating groups, so it is a weaker base than dipropylamine. And like if I'm going too fast, if this doesn't make sense, like feel free to ask me to clarify in another way. Because I want to make sure like it makes sense to everybody who's not sure. Okay. Next one is aryl amines, such as aniline, are weaker bases than alkyl amines. Do that over here. So like this is aniline. You've seen it before. You should be familiar with the name and structure. And then this is just a regular alkylamine. Like you can refer to pK values from like that table and the slide from lecture, but you can also just think about like effects that might be different between these two that might affect the base strength. Remember, they have lone pairs. What might the lone pairs do in these? give it 10 or so more seconds. Okay. So you guys are evenly split on this one. What I was trying to hint at is this resonance in aryl amines, because you have a lone pair right next to the benzene ring. So you can draw a resonance form, and then you can draw a couple more. I'm not going to draw all of them. The point is these have resonance forms. So resonance, and alkylamines don't. Resonance. Like we said earlier, resonance forms makes something more stable, so it's less reactive, which would mean it's a weaker base because of the resonance. Resonance. Than an alkylamine because of the lack of a resonance form. So saying aryl amines are weaker than alkylamines is true because of all of that I just discussed. Okay. Next one is E. Reduction of a nitrile yields a secondary amine. So this is a nitrile carbon-nitrogen triple bond. And like we'll talk about the conditions later, but like if we're reducing it, it's saying you're going to get a secondary amine as the product every time. So I'll give this like 10 or so more seconds. And I just want to say, as a general tip, if you're ever like looking at true false questions on a test, like the kinds of things I'm doing to give you hints are things you could do to help yourself, like try to draw out what he's describing, because a lot of the time, like it might sound like just a conceptual question, but if you draw it out, you might like see something that rings a bell, and then you'll be able to figure it out. Like drawing out this reaction might help you recognize that if you were going to reduce the nitrile here, like you're basically adding hydrogen across the triple bond. And if you're just adding hydrogen and you're not like adding carbons or anything, like you're going to end up with a structure like this, right? Because we're just adding hydrogens here, basically, to both sides of it. And what kind of amine is this that I drew as the product? Is this primary, secondary, tertiary? What does it look like? How many bonds? Yeah, it's primary because there's this one carbon-nitrogen bond. So it's a primary amine. And regardless of what the nitrile is, this is always what you would get. You'd get a primary amine. So like that's the kind of thinking that might help you work through a problem if you're not sure how to do true false on a test. So this one was false because it said it would form a secondary amine. It will be primary. Secondary. And last one is F. Azides can be reduced with NaBH4 or LiAlH4. And azides are reduced with similar conditions to nitriles. So like we'll talk about it a bit later, but go ahead and end this one. Guys are evenly split on this. So like I'll just take the example I have up here with the nitrile already. If we wanted to reduce the nitrile, we could only use LiAlH4. And there's more to the conditions. It's not just LiAlH4 by itself, but this is the only reaction that works. NABH4 won't reduce nitriles and azides. So this one was false because of that. The LiLH4 will work. Okay, so that's number one. If you have any clarification questions at all, like please ask so we can make sure you understand. Otherwise, I'll just keep going to the next one. As usual, just stop me at any point, even if you're interrupting me, if you have a question. So this one, we're looking at the base strength of these amines. And for the true false question, I already kind of talked about how we can approach this. Remember, I said electron donating groups make bases stronger and electron withdrawing groups make bases weaker. So that's the kind of logic we can use to approach this. And like I discussed how alkyl groups are donating groups, and I pointed out how halogens are withdrawing groups. So like these things on the left, the first three all have ADGs, and then we have NEWG with the halogen here on the right. So with that in mind, can anybody give me like from left to right the base strength of these? Or if not, could you tell me which one is the strongest base? 3214 is good. And just to briefly go over it to make sure everybody understands, like this is the strongest because it has the most donators. So because it has a lot of donating groups, that makes it a very strong base. This is the weakest because it has a withdrawing group and the other ones don't have a withdrawing group. And then the other two, it's a difference of 2 EDGs versus 1. So that makes the one with 2 groups stronger. Okay. So that was number 2. I'm gonna go ahead and erase this and scroll down to number 3. But again, if you have a question, feel free to ask. So here we're looking at aniline with different functional groups paired to it, and these will affect its base strength. And when you're looking at these, it's the same kind of logic like as what we were just doing. Remember, EDGs make bases stronger, EWGs make them weaker. It's the same logic, just in the context of benzene rings. What's a donating group and what's a withdrawing group can change a little bit. And remember, you can like identify a donator versus a withdrawer by like calling back to this sort of, it's like a rough sketch of that reaction trend arrow for EAS reactions. Remember stuff over here on the left, these were electron withdrawing groups. And then stuff on the right were electron donating groups. So like if you remember where a functional group falls on this, then that can help you figure out both how it affects EAS reactions and how it affects acids and bases like this. So let's start with the one with a methyl group. Where does the methyl group show up on this diagram? Like, is it donating, withdrawing, somewhere in the middle? Where does it show up? Right side, yeah. Because a methyl group, you can call it an R group. It's just like an alkyl group, and it's weakly donating. What about the nitro? Where does this show up? Far left. This one just has a hydrogen here, and hydrogen kind of shows up at this dividing line between the donators and withdrawing groups. So that's where that shows up. And then where does this ester show up? And this is probably the trickiest one. Yeah. Esters can be withdrawing. It depends on how it's attached to the benzene ring though. So like there's two different ways this could be attached. It can be the way that it is down there, or it can be like this with the carbonyl carbon attached to the benzene ring. But this makes a huge difference in like its effects on donating and withdrawing. Here, like what's attached is the oxygen, which has lone pairs on it. And this might sound familiar. Remember, like when the thing attached to the benzene ring has lone pairs, it donates electrons by resonance. That's part of what makes a lot of the stuff on the right side of the diagram a donator. And then if the thing attached to the benzene ring has a double bond on it, like a carbonyl, then it withdraws electrons by resonance, because you can like push electrons towards it and then push electrons up towards the thing, the oxygen up there. So it's pulling electrons out of the ring. Like with the carbonyl attached, it's an electron withdrawing group, but with the oxygen attached, it's a donator. But this is the same functional group. So like this is something we saw at the beginning of the semester, but like it's relevant for this and like just for old material in general, because the final will be cumulative. So hopefully this is a bit familiar. And this is where the ester would show up, because it's a relatively strong donating group. So I will say like that was the trickiest part of this question, because esters can be withdrawing or donating. You have to pay attention to how it's attached like this. Now with all of this in mind, can anybody tell me like from left to right what the number of these should be? Like how should we rank them? Yep, 2, 4, 3, 1 is good. And I'll go over it pretty quickly. Like if EDGs make bases stronger and EWGs make them weaker, then basically like either have a mental picture of this diagram in your head or actually just write it out. That might make it safer. And then when you write it out like this, just go from right to left. Right side is the most strong base, left side is the weakest base. So like if you just go like that, then you're pretty much golden. So yeah, this is how you should approach these. And just a quick aside, these are like the opposite trends of what we saw for acid strengths. It's like when we were looking at acids, electron donating groups made them weaker. And then EWGs make acids stronger. It's the same logic, because like to look at the acid strength, I can just draw one here. But to look at the acid strength, like remember, we would look at the conjugate base form. And then we would think what is going to make that base a stronger or weaker base, like relative to other bases. And the halogen there is a withdrawing group. So it pulls electrons, it makes the base weaker. And then that ties to the idea that like stronger base goes to a weaker acid and weaker acid. It's like if you have a withdrawing group that makes the base weaker, so the acid was stronger. That's why these are like exact opposites of each other, because it's the same ideas with both. So like I would just recommend trying to understand the logic behind like how the groups affect bases, and then remember this idea. And I think like then it might be less confusing than trying to remember how they just flip depending on what you're looking at, because they are connected. Hopefully that kind of makes sense. Okay, gonna go ahead and erase this and move on to the last one on this page. Here we just have a couple of different functional groups, and you should have rough ideas of pK values for all of these. And this is a question you might get asked on a test, so it's good to be able to recall them. So before ranking them, I'll go ahead and list the PKs or ask you guys first. What general number should you think of when you have an amine for the PK? That's okay. This one is about 35. It's on the high end because this is a pretty good base. It's not a good acid, so it has a high pK. How about a carboxylic acid? Does anybody remember pK for these? Yeah, that's 5. What about an alcohol? Yep, 16. And then a regular carbon-hydrogen bond. Yeah, very high. It's basically not acidic at all. But the number Okuda told you to know is like 50-ish. So that's a number you could put on a flashcard because you might be asked to recall it like this. And then for a question like this, like you just have to remember the pK values and then know that low pK means stronger acid. So you're just going from low pK to high pK to rank these. So then this would be 1, this is 2, 3, and 4. So I realized I was emphasizing acid-base stuff a lot on this page. Like I'm not going to say it's going to be a huge part of your final, but you probably know the drill by now. I'm sure you had at least one acid-base question on every exam. So you should expect like 1 or 2 at least on your final. And since you just learned about amines, it might be more likely to be about amines like these. So good to be prepared. Now here we are, well, I'm giving you a reaction. Like I'm saying, adding this alkyl halide to ammonia will give you this product. And it's going to do that, just to show you, through an SN2 mechanism. But then it's asking if the product shown is the only one that would form, and if not, what else would form. So first question, is this the only one that's going to form? Can anybody tell me consider like how reactive the product might be and that it still has a lone pair. So he might ask a question like this on a test. Like he likes to ask questions where he says there's something wrong with a reaction and you have to explain what it is. So this could come up in a question like that. The problem with this is like once you add the alkyl group, remember this is an electron donating group. So it's donating electrons to the nitrogen. And then if you're donating electrons, that means it has more electrons to give away as a nucleophile. So it's going to be a stronger nucleophile. And then it's going to be more reactive than how it started. So Ag makes reactive. So basically, once you add one group, it's more reactive than it was when it started. So then it's going to want to react again. And then this is even more reactive than the last one because now we have two donating groups. So it's going to want to react again. And then this is more reactive than the last two because it has free donating groups. So it's going to react again. And basically you end up with a mixture of products because it becomes more and more reactive. And this is similar to an issue we saw with Friedel-Crafts alkylation at the beginning of the semester. Remember, like, if you started with benzene and you did a Friedel-Crafts alkylation, like say you added an ethyl group. I remember ethyl groups are electron donating groups, so they make the benzene ring more reactive than it was when it started. So then you would add another one, and then you could add more and more and more. Like you'd get a mixture of products, just like we do here. So it's the exact same idea, making it more reactive, so you can't stop it. And you should be aware of this idea because he might ask you to explain this issue in some form. All right. So if there are any questions, feel free to ask. Otherwise, I'll keep going to the next one. So here we're starting with an alkyl halide. And in the first step, we're adding Na and free, and then we add LiAlH4 and THF and last acid. First, what is the first step going to do? This is the structure. No, but this is the structure because the sodium is just a counter ion for the negative charge. So that's the N free from the first step. What do you think this would do with the alkyl halide we're starting with? What do nucleophiles usually do when we have a carbon bonded to a halogen like this? Yep, it does an SN2 mechanism. And then that will attach like an N-free group, basically. That is an azide. So this was sodium azide, and now we have an azide attached. And then we add LiAlH4 and acid, What's are these two going to do to the A side? And yeah, reduce it. And what's it gonna get reduced to? Yep, a primary amine. It basically just replaces the azide with an amine. And I believe you'd get nitrogen gas as a byproduct. I am not 100% sure about that, but I think you would. It would make sense. But what you care about is the fact that you get a primary amine. So if you were doing this on a test, unless he asks you to, you don't have to show the intermediate. I just did to show you like it's doing an SN2 mechanism, and then you're reducing the intermediate you get. And it's important to remember that this is an SN2 mechanism. So it wouldn't work with tertiary substrate. That wasn't the case here because this is secondary. But if it was tertiary, this wouldn't work. So it's important to remember that. And then every single time you use this reaction, the product will be a primary amine. So if you want to memorize that, you can. I think it kind of just makes sense. Like if this is your intermediate and you reduce it, you should end up with a primary amine. But if you want to memorize that, you can too. Okay. Next one, we're starting with an OTOS as our functional group, which is similar to a halogen. Like we can use that as a leaving group. And we're ending up with an amine, and we added 1 carbon in the process. So 1 carbon. So how can we do this? We can't use an azide like the last one because that one didn't add any carbons, and we want to add a carbon. But what's something I brought up earlier that adds a carbon, and then we can reduce it to make a primary amine? If we added nitrile. It's a nucleophile we've seen before, right? It can do an SN2 mechanism just like the last one did. And then there's a carbon here, so we're adding a carbon. And I brought up in the true false that if you reduce a nitrile, you get a primary amine, which is what we have here. So once you add the nitrile, you just have to reduce it the same way we did in the last one. So both of these reactions, using an azide and using a nitrile, will give you a primary amine. The difference between them is just one of them adds a carbon, one of them doesn't add a carbon. So they both have uses, it depends on the context. But they're not interchangeable. Okay. Next one, we have this structure with a cyclic amide and kind of attached to a benzene ring. And then we're adding KOH, then an alkyl halide, and then sodium hydroxide, water, and heat. There are some details to this that you can rationalize. I'll just talk about the first two, and then like if you want to, or if you're curious, I can explain the last one, but you don't have to know it. But in the first step, we're adding hydroxide, what can hydroxide act as? Like, in general, what have we seen it act as in reactions? Nucleophile, electrophile, acid, base, other things. What is hydroxide? Has a negative charge, so yeah, it can act as a base. It can be a nucleophile, but in this context, it's going to be a base because we have this hydrogen here on the amide that's relatively acidic, so we can take that. I'm going to draw this over here. It's going to act as a base. It's not an oxygen. And then you're going to form this intermediate where you have a negative charge on a nitrogen. And then this can act as a nucleophile because we have a full negative charge. Anything with a negative charge is a pretty good nucleophile. We have an alkyl halide right here. Just like earlier, like this is going to be a good electrophile. So we can do an SN2 mechanism between these two. The amine can attack and displace the chlorine. Or not amine, but the nitrogen will attack it. And then I won't like go through the details of a mechanism or anything, but I guess I'll just say, and if you're curious, again, like I can talk about it more or you can look into it. But these conditions in the last step are for hydrolysis of the amides. Because it's basically like there's two amides attached to each other. And remember, if we had these conditions with a regular amide, you do hydrolysis, you turn it into a carboxylic acid. And it's the same thing here, because like this is an amide, and then the carbonyl of the nitrogen on the bottom is also an amide. So when you do hydrolysis, that leads to this structure forming. You get carboxylates where the amide was. And then you kick out the nitrogen along with anything attached to it when you did hydrolysis. So when you do that, you end up with this amine from this particular reaction. And there's a name for this reaction. Does anybody remember what it is called? If not, that's okay. Names kind of suck, but you do have to know them. It's okay. Yeah, this is Gabriel. Amine synthesis. And just like the last two reactions, this will always give you a primary amine. Just because of how you make the amine, it's always going to be a primary amine. So if you want to remember that, feel free to. That one's not exactly as logical as the last two, so yeah, might be good to know. And okay, I'll just clear the screen. I just want to say that like when you're doing a Gabriel synthesis, this part, the starting material, is always going to be the same. And so is this and this. Like the starting material and the first and third step are always going to be the same. The only difference is going to be like this second step. What is the alkyl halide you're adding? And that affects like what amine you form. So that's really the only difference. Everything else is always going to be the same. So if you see like a structure like this and 3 steps, you should immediately think Gabriel synthesis and trying to make a primary amine. But you should also remember at least like that first step leading to the negative charge on the nitrogen. And then remember it did an SN2 mechanism. So because it's SN2, there might be limitations, and you have to remember that it might not always work because of that. Okay. So here's another Gabriel synthesis, because we have that starting material and this first and third step, same as the last one. Here is our substrate we're adding, and we're trying to make an amine out of. Can anybody tell me what kind of substrate that is with the red next to it? Yep, it's tertiary. So this time that's an issue, right? Because SN2 mechanisms don't work with tertiary substrates. So like, I'm not gonna go through all the details, but remember it forms a negative charge. But then you have a tertiary thing, so it's not gonna work. You might be able to put no reaction, that might be okay here. But typically if you have a tertiary substrate and you're trying to do SN2, it's gonna do E2 instead. So you would probably end up with this E2 product. But either way, it's not doing what you wanted it to do. So that's an issue. All right. So just don't forget that Gabriel is an SN2 mechanism. Now here we're starting with an aldehyde, and we have pH 4.5, and then we're adding ammonia. And let's ignore the second step for now. This first step is something we've seen before. What kind of functional group is that going to lead to? It's the same thing we would get like, yeah, specifically in imine, yeah. Imine versus enamine depends on the amine you add. Remember, if it's NH3 or a primary amine, it'll give you an imine. And then if it's a secondary amine, it'll give you an enamine. And this is with that like pH 4.5 condition. And then it's with a ketone or an aldehyde. So it depends on what we're adding. Here it's NH3, so yeah, it'll give us an imine. Looks like this, that's the intermediate you get. And then what is NABH4 going to do to this? I know we haven't seen it in this context before, but we have seen this reagent before. What did it do in the past? What kind of reactions? Like, say I had an aldehyde. Yeah, it does reduction. If you added NABH4 to just an aldehyde, remember it would reduce it to an alcohol. These aren't the full conditions. I guess I'll just put it. It would be more like this with acid as a second step, but it reduced stuff in the past, and it's going to be a reducing reagent here. So we're reducing the imine. We're basically adding hydrogen across the double bond. And when we do that, we end up with an amine, which is a primary amine here. Because basically we just added hydrogens like here and here across the double bond, which means like you just got rid of the double bond basically, and you get primary amine. Okay, So this is another way to synthesize amines. The next one is similar. We're starting with a ketone instead of an aldehyde, but same kinds of conditions. So this is a primary amine, which means like, again, it's going to give us an imine as the product of the first reaction. It will look like this. And then this is a different reagent from the last one with NaBH4. But what does this look, or maybe not what does it look similar to, but like we've seen hydrogen with metals before. What did conditions like this do in the past? Like what kind of reactions? Like reduction, yeah. Like one that comes to mind is like if you have a benzoic carbonyl like this, and if you added hydrogen and a palladium catalyst, that would reduce the carbonyl, remember? So hydrogen with metals typically does reduction, just like NaBH4 typically does reduction. So that's what's going to happen here. It's going to do the same thing NaBH4 did and the last one. It's going to reduce it to an amine, not an enamine. I'm just going to erase this so it doesn't get too crowded. And that's the product you get. And I didn't really emphasize this up to this point, but all of the amines and the reactions that we were doing before, like you always got a primary amine. That's what a lot of the reactions you're learning do. Most of them make primary amines. But this amine that I just drew is secondary. So this is one way that you can make a secondary amine, by like starting with a ketone, adding a primary amine to make an imine, and then reducing it. You get a secondary one. And that just might be something that's good to take note of because, like I just said, most of the reactions make primary amines. Like if you have a synthesis and you want to make a secondary amine, then your options are kind of limited, which makes it a bit easier to think about how to approach it, I think. And I don't have an example of this, but you can also do this with enamines if you add a secondary amine to a ketone or an aldehyde. So don't forget about that. And the last one here, we are starting with an acid chloride. And in the first step, we had two equivalents of an amine, and then we had LaLH4 and an acid. What is this first step going to do? What kind of functional group will that lead to? I'll say it's some sort of carbonyl. An amide, yeah. That is, like these specific conditions with an acid chloride will give you an amide. And then we've seen these conditions with amides before. What happens if we reduce an amide like this? What kind of products do you end up with? Steps 2 and 3. If you don't remember, that's okay. When you reduce an amide with LaLH4, it gets reduced to an amine. It basically just gets rid of the carbonyl. So this is what you'd end up with. And this is a tertiary amine. So this is a way to make a tertiary amine. Along with like if you went through an enamine intermediate and you reduced it, you'd get a tertiary amine. This is another way. So just another thing to take note of. Making an amide and then reducing it is a way to get something that's bigger than a primary amine. Okay, go ahead and move on to the next one. So you don't have to know a mechanism for these two, but there are names to both of them, and you should know like what the product is and what the byproducts are. Can anybody recall what it will be for the first one? Like what kind of products do we end up with and what kinds of byproducts do we get? And if you don't know it yet, like that's okay. This one is pretty weird. Like it doesn't really seem like it matches the reagents. I would suggest using flashcards to memorize this. So I don't even know the mechanism, so I can't like explain it logically. Like I just said, I suggest memorizing it. But basically you're gonna lose the carbon in the carbonyl as carbon dioxide. That's a byproduct in this reaction. So I'll just start by drawing that. Like you lose carbon dioxide as a byproduct. And then because you're losing that red carbon as carbon dioxide, like you're losing one carbon in the process. So we started with 4, we end with 3. And then you also end up with an amine. And specifically, it's a primary amine. And you're always going to get a primary amine from this. So just remember that if you start with an amide and you use these exact conditions, you lose one carbon as carbon dioxide, and then you get a primary amine. And this reaction has a name. It's called a Hoffman rearrangement. And the next one is actually pretty similar. Like the starting material looks very different. You have an azide instead of an imine attached to the carbonyl, and you have different conditions, but it's actually going to do nearly the same thing. You're going to lose the carbonyl carbon as carbon dioxide. And then if you look at this, like you have 2 nitrogens there. So like you can imagine like you're going to lose them probably, and you lose them as nitrogen gas. So that's another byproduct of this one. And then because we're losing that red carbonyl carbon, you're losing one carbon and then you form an amine. So we started with 2 carbons attached to the benzene. Here we only have 1. And we have our amine, which again is a primary amine. You always get a primary amine from this. And this one also has a name. It is called a Curtius rearrangement. I might be mispronouncing that, but that's how you spell it. So 2 different starting materials and different conditions, but they do very similar things. So maybe try to lump them together when you're trying to memorize this. And again, like I don't know a mechanism for this, so I can't walk you through it. You can look into it if you're curious, but you won't be asked to recall it. Okay. Next one, we're starting with an amine. And for this first reaction, we're adding HNO3 and H2SO4. Can anybody tell me what product or products we would end up with from this reaction? Have we seen this before? That is what it looks like. So this is an important distinction, and this is actually why I put this here. If you use HNO2 on an amine, that'll form a diazonium salt. That's the N triple bond structure you're thinking of. But if you use HNO3, which is what we have here, it'll do a different reaction. Yeah, it'll do nitration. So they look very similar, and it sucks they both even use H2SO4, but they do very different things. So yeah, this is nitration. We're gonna add a nitro group. And where is the nitro group going to end up relative to the amine? Is it going to be ortho, meta, para, some sort of combination? It's going to happen. What kind of director is an amine? Yep, it's ortho para. Remember this little crudely drawn arrow. This is where NH2 shows up, and stuff on the right side is ortho para directing. So it will direct the nitro group to go to these two positions. And you should draw both products if you have an ortho para director, like this. So very similar to that reaction you just saw Tuesday now, but don't forget about nitration. And on that note, don't forget about the other EAS reactions, because the final is cumulative. It's very likely you'll have at least one or two benzene reactions pop up. Okay, next one, we're starting with a nitro group. And first we have hydrogen and palladium, and we have HNO2 and H2SO4, and then copper nitro and potassium nitro. So one step at a time, what is the hydrogen and palladium going to do? What kind of functional group is this going to lead to? And consider that this is reduction, so yeah, it's going to reduce it to an amine. So that is the first step. And then here is HNO2 and H2SO4. So with these conditions, I'm gonna scroll up a bit. But with these conditions, it's not gonna do nitration, even though it looks similar. It's gonna form a diazonium salt. Just after step 2. You end up with this. And this is important because if you look at this, nitrogen triple bonded to another nitrogen, that's just dinitrogen gas, which is a very stable leaving group because it's in the air. We breathe it all the time. So it's very stable as it is. So like, it's just good to recognize that like this diazonium salt is a good leaving group. And then basically, if you add a nucleophile to it, you kick out the leaving group and replace it with the nucleophile. So that's what like the series of reactions that involve this do. They kick out the leaving group. And you don't have to know a mechanism for how it gets kicked out. You just should know like that's what's going on. So like for this one, we have copper nitrile and potassium nitrile. So what kind of functional group are we going to end up with if we add this to diazonium? Yeah, a nitrile. Some of them are pretty like with the nitrile being in both things, and it's kind of similar to this one with bromine. Like these are easier to remember, I think, than some of the others. But yeah, good job. And then might be good to point out you get nitrogen gas as a byproduct. Okay. Just gonna move this up a little bit. Right. Next one. Oh, actually, before I do that, there's a name for these series of reactions with like the diazonium salt as an intermediate. And I know like we've talked about a lot of named reactions today. It kind of sucks, but it is what it is. Flashcards are your friends. These are called Sandmeyer reactions. And this is referring to like when you have a diazonium salt as an intermediate. Okay. Here we have a fill in the blank. We're starting with the diazonium intermediate and we want to make a phenyl. I will say the conditions for this are a little all over the place and actually pretty long time. So I'm just going to fill it out. This is one, like I'm suggesting it a lot, but like some things you just kind of have to memorize and there's not a lot of rhyme or reason to it. So I think flashcards can help you a ton of stuff like that. Just to stick it down. These are the conditions that you need to turn a diazonium into a phenyl. Next one, we're starting with an amine. First, we're adding HNO2 and H2SO4. That'll turn it into a diazonium salt. And then we have HBr and CuBr, so kind of similar to the nitrile. It's going to end up putting a bromine there. And just for the sake of completion, if you had like the same first step and then you had HCl instead of HBr and CuCl instead of CuBr, like the copper and the bromine are interchangeable. You end up with a chlorine attached. So adding a bromine and the chlorine through a diazonium intermediate are basically identical. All right. And the last one, we have an amine and a methyl group. And at the end, we want the amine to be gone completely. We just want to replace it with a hydrogen. So to kick it out, you have to turn it into a better leaving group first. So you would want to add HNO2, and H2SO4. Same thing we're doing with most of the other ones. And then the conditions to kick out diazonium and add a hydrogen are H3PO2, this acid. So these are most of the reactions that you need to know with diazonium. The only other one, I'll just put it here. If you add sodium iodide, NaI, like this, it puts an iodine there. So that's the only one I don't have an example of, but there it is. That's all 5 reactions with these diazonium salts that you need to know. And especially the nitrile and the phenyl, like those are reactions that actually I don't think you ever learned how to make a nitrile directly. So that's good to take note of. Like that might be useful in a synthesis since I don't think you have another way to make them. And then phenols, you have one way to make them, but I think this is an easier one. So another thing to take note of. Okay. Last one. Here are some sugars, and I'm saying to basically give a general identification of them. Like as an example, I'm saying like this is a kind of answer you would give L-aldotriose, and just to like show you what that would look like so it's easier to walk through these. The aldo part is saying that there's an aldehyde in the structure. So here's an aldehyde. Triose is telling us there's 3 carbons. So there's 1 for the aldehyde, 2, and then 3. And then the L, there's only 1 chiral sensor here, but I'll explain it again with the other ones. But the L is saying that one particular chiral sensor, the alcohol, is on the left. There's only 1 here, so it's a little easier with this one, but I'll explain it with the others. But like the alcohol being on the left here is what makes it L. This is what makes it an aldo. And then there's 3 carbons, so that's what makes it a triose. So that's the kind of thinking that you should have to approach the other ones. Now, in terms of like determining if it's L or D, like those are the 2 designations, you should look at the chiral sensor that's at the bottom of the structure. So you're looking at the one I circled in red in these 2. It's like, you're not looking at this carbon. This is the carbon like at the very bottom of the structure, but you want to look at the chiral sensor that's at the bottom. So that's why you're looking at the one I circled. L versus D. And then, like I was saying, with the L-aldotriose, if that alcohol at the bottommost chiral sensor is on the left, then it's L, like this one. And if it's on the right, then it's a D sugar. So that's how you distinguish them. And in terms of remembering that, like I think it's easy to say L goes with left. Like probably already noticed that, but just in case you didn't, like that's an easy way to remember them. And then D is just the other one. And then in terms of aldose versus ketose, you're looking for an aldehyde or a ketone, which we've looked at these functional groups a lot this semester, so that's not too bad. And then the number of carbons, you just have to make sure to count it correctly. Okay, so for this first one on the left, is this an aldose or a ketose? What kind of functional group? It's a ketose because we have a ketone here. And then how many carbons are there in the structure? Yeah, 5. Because there's more. 1, 2, 3, 4, 5. So it's going to be a pentose. And then is this a D or an L sugar? Yeah, it's D because the alcohol at the bottommost chiral center is on the right. So then you would call this a D keto pentose. Right. Next one, what kind of functional group do we have? Aldehyde, yep, so it's an aldose. How many carbons are there? 1, 2, 3, 6. And is that a D or an L sugar? Because the alcohol is on the left at the bottommost chiral center. So you would call this an L aldohexose. And like these aren't the only examples of like D ketopentoses and L aldohexoses. So like I'll just say, I remember on one of my exams, like I had a question that was somewhat similar to like draw an example of like an L aldohexose. Yeah, you have to know the structure of glucose. That's the only one you have to know. And that one is a D, has 4 chiral centers. I'll just draw it for you. I would recommend like drawing it a bunch of times until like you have it committed to memory. But this is what it looks like. And then the other stuff is hydrogens. So I'll put them in now. This is the only one you have to know. And on that note, like maybe he could say as a question, like draw D glucose and then tell me like, give an identification for it. Is it a ketose? Is it a pentose? And how many carbons is it? So like we can do that here. It's an aldose and it's a hexose. So this is a D aldohexose. And I wouldn't necessarily memorize like glucose is an aldohexose, but you should know the structure. And then from that, you can figure out what it is. And I think I was going to say something else, but I can't remember. Just, oh, like he could ask you to draw some random structure, like a question, instead of saying like, what is this? An aldose, hexose, what is it? Like he could say, draw an example of an aldohexose. And this isn't the only one. Like, all that you need to make it an aldohexose is 6 carbons and aldehyde, and then the alcohol at the bottom has to be on the left. But then the rest of the chiral centers don't matter at all. You can put whatever you feel like putting. It doesn't have to be like left, right, left, like I gave in the structure. They could all be on the right. They could all be on the left. It could be some sort of mixture. It doesn't matter. So like if he asks you to draw an example of something, you can put whatever you want. Unless he asks to draw glucose, then you have to draw that exact structure. And then I don't think I'll go into it today. I might during the review session, but you talked about Fisher projections today, I'm assuming. He might ask you to like tell him like at this chiral center, I'll do it in a different color, but like at this chiral center, like what is the stereochemistry? Is it R or is it S? And you should be able to tell him that. So that's another thing he might ask about these. But okay, I've talked you guys' ears off enough. I'll send something out about a review session either today or tomorrow probably, and hopefully see you there. If not, good luck. I hope you had a good semester, and yeah, have a good weekend.